Algebraic operations in component form. Welcome, everyone. Today, we are moving into a very practical part of our study, algebraic operations in component form. Now, before we dive into the new material, let's take a moment to reflect on what we have already covered. In our previous lessons, we learned how to represent a vector within a three-dimensional coordinate system by using what we call the standard basis vectors, I hat, j hat, and k hat. These vectors serve as our fundamental building blocks for direction in 3D space. The reason this is so important for today's lesson is that once we express our vectors in this specific component form, the math becomes much simpler. Instead of dealing with complex geometric drawings, performing algebraic operations becomes a very straightforward process. It essentially boils down to just manipulating the individual scalar components, the numbers attached to our I, j, and k, one by one. So, let's get started with how we actually define these vectors mathematically. Vector representation. Now that we've established that we can represent vectors using the standard basis vectors I hat, j hat, and k hat, let's look more closely at how we actually write them down. To prepare for our algebraic operations, let's consider two general vectors, vector A and vector B. We can define vector A as a sub-1 I hat plus a sub-2 j hat plus a sub-3 k hat. Similarly, we can define vector B as B sub-1 I hat plus B sub-2 j hat plus B sub-3 k hat. In this notation, the terms a sub-1, a sub-2, and a sub-3, as well as B sub-1, B sub-2, and B sub-3, are what we call the scalar components of vectors, A and B. Think of these as the specific numerical values that tell us exactly how far the vector extends along the x, y, and z axes. Keeping these individual components in mind is crucial, because as we will see in the next few slides, performing operations like addition and subtraction is really just a matter of working with these individual numbers. One vector addition, sum. When we work in component form, vector addition is quite intuitive. You simply perform the addition by adding the corresponding components of the two vectors together. The reason this works is based on a fundamental principle. Components that lie along the same axis can be added algebraically. In other words, we only combine the I components with I components, j components with j components, and so on. To put this into a mathematical rule, here is the formula. Vector A plus vector B equals the quantity A sub-1 plus B sub-1 multiplied by I hat plus the quantity A sub-2 plus B sub-2 multiplied by j hat plus the quantity A sub-3 plus B sub-3 multiplied by k hat. Now that we have defined our two vectors, let's look at how we actually combine them. The first major operation we'll cover is vector addition, or finding the sum. As you can see, it's just a matter of grouping the matching parts. We'll see a practical example of how this applies to a moving drone in the next slide. Real-world example of vector addition. Now, to help you visualize how the addition we just discussed works in practice, let's look at a real-world scenario. Imagine a drone navigating through three-dimensional space. Suppose the drone starts at an initial position and first moves according to vector A, which takes it from its starting point to a specific point. Let's call it point A from that point A. It then undergoes a second movement, following vector B, which carries it from point A to a final destination, point B. If we want to find the drone's total displacement, that is, the direct straight-line path from the very beginning to the very end, we simply find the sum of these two vectors. This perfectly illustrates why adding the components of vector A and vector B gives us the resultant movement. Step-by-step calculation for vector addition. Suppose we are given two vectors, vector A, which is 2i plus 3j minus 1k, and vector B, which is 4i minus 1j plus 5k. To find the sum, we simply follow the rule we just discussed. We group the like components. First, let's add the I components. 2 plus 4 gives us 6. Next, we move to the j components. 3 plus -1 results in 2. Then, we handle the k components. -1 plus 5 leaves us with 4. Finally, we combine these individual results back into a single vector. So, vector A plus vector B equals 6i plus 2j plus 4k. As you can see, it really is just a straightforward process of adding the corresponding parts. Now that we understand the theory behind adding vectors, let's walk through a concrete calculation together to see how this works in practice. In the next slide, I'll show you how we can apply this same logic to a real-world scenario involving a drone. 2-vector subtraction, difference. If you think back to basic arithmetic, subtracting a number is the same as adding its negative counterpart. The same principle applies here. In vector terms, subtracting vector b from vector A is essentially the same as adding the negative of vector b to vector A. To perform this operation in component form, we follow a very similar pattern to the addition we just saw. To subtract vector b from vector A, you simply subtract each corresponding component of vector b from the components of vector A. You handle the I components together, the j components together, and the k components together. Let me write out the formal formula for you. Vector A minus vector b equals the quantity A sub 1 minus b sub 1, all multiplied by I hat, plus the quantity A sub 2 minus b sub 2, all multiplied by j hat, plus the quantity A sub 3 minus b sub 3, all multiplied by k hat. Now that we have mastered how to add vectors, let's look at the second operation, vector subtraction. As you can see, it is a very systematic process. In the next slide, I'll show you a real-world application of how this subtraction helps us find the relative position between two moving objects. Real-world example of vector subtraction. Now, let's step away from the abstract formulas for a moment and look at how vector subtraction actually applies to the real world. Imagine you are an air traffic controller monitoring two different aircraft. Suppose vector A represents the position vector of an airplane located at point A, and vector B represents the position vector of a second airplane at point B. If we perform the operation, vector A minus vector B, the resulting vector doesn't just give us a random number. It specifically represents the relative position of airplane A with respect to airplane B. In other words, it tells you exactly how you would have to move from the second plane to reach the first one. This concept of relative position is a crucial application of the subtraction we just calculated in the previous step, and it sets the stage for our next slide, where we will work through a concrete numerical example to see this in action. Step-by-step calculation for vector subtraction. Suppose we have two vectors, vector A, which is 5i plus 2j plus 8k, and vector B, which is 2i minus 3j plus 4k. To find the difference, we simply follow the rule of subtracting corresponding components. First, let's look at the I components. We take 5 and subtract 2, which gives us 3. Next, we move to the j components. This is a crucial step where you must be careful with your signs. We take 2 and subtract negative 3. Remember, subtracting a negative is the same as adding, so 2 plus 3 gives us 5. Then we handle the k components. 8 minus 4 leaves us with 4. Finally, we combine these individual results back into a single vector. Our final result for vector A minus vector B is 3i plus 5j plus 4k. Now that we understand the theory behind vector subtraction from the previous slide, let's walk through a concrete calculation to see it in action. As you can see, it is a very systematic process of working through each axis one by one. 3. Equality of vectors. Now you might be wondering, what does it actually mean for two vectors to be equal? In geometry, we know that two vectors are said to be equal if and only if they have the exact same magnitude, meaning their length is identical, and the exact same direction. But here is the beauty of working in component form, which we've been using throughout this lesson. Checking for equality becomes much simpler. Instead of measuring lengths and angles, we just need to look at the individual parts. In component form, this means every single corresponding component must be identical. To put this into a formal mathematical condition, Vector A equals vector B if and only if a sub 1 equals B sub 1, a sub 2 equals B sub 2, and a sub 3 equals B sub 3. Now that we have mastered how to add, subtract, and scale vectors, let's look at a very important concept: equality of vectors. Essentially, if even one component is different, the vectors are not equal. This principle of comparing components one by one is a theme we will continue to use as we move into our next topic, scalar multiplication. 4. Scalar multiplication. Think of a scalar as just a regular number, which we'll represent with the Greek letter lambda. When we multiply a vector by this scalar lambda, the rule is very straightforward. You simply multiply every single component of that vector by lambda. It is important to understand the effect this has on the vector itself. This operation changes the magnitude or the length of the vector. If lambda is greater than 1, the vector stretches. If it is between 0 and 1, the vector shrinks. Furthermore, pay close attention to the sign. If lambda is a negative number, it will not only change the size, but will also reverse the direction of the vector, pointing it in the exact opposite way. To put this into a mathematical formula, if we have a vector A with components a sub 1, a sub 2, and a sub 3, then lambda times vector A is equal to lambda times a sub 1 in the I direction, plus lambda times a sub 2 in the j direction, plus lambda times a sub 3 in the k direction. Now that we have mastered how to add and subtract vectors by combining their corresponding parts, let's move on to our fourth operation, scalar multiplication. In the next slide, I will show you a real-world example involving a car's velocity to help you visualize this concept in action. Real-world example of scalar multiplication. Now, to help you visualize how scalar multiplication works in a practical sense, let's look at a real-world scenario. Imagine a car traveling along a road with a specific velocity vector, which we will call v if the driver presses the accelerator and doubles the car's speed, but keeps the steering wheel perfectly straight so the direction doesn't change. The new velocity is simply 2 times the original vector v. This perfectly illustrates our previous point. Multiplying by a scalar changes the magnitude, in this case, doubling the speed, without altering the direction of the vector. Step-by-step calculation for scalar multiplication. Suppose we have a vector, let's call it vector A, which is defined as 3i minus 4j plus 2k. We are going to multiply this vector by a scalar lambda, which is equal to negative 3. First, let's look at the I component. We multiply negative 3 by 3, which gives us negative 9i. Next, we move to the j component. Be very careful with your signs here. We are multiplying negative 3 by negative 4, and since 2 negatives make a positive, we get 12j. Finally, we handle the k component. Negative 3 multiplied by 2 gives us negative 6k. When we combine all these results back into a single vector, our final answer for lambda times vector is negative 9i plus 12j minus 6k. Now that we understand the concept of scalar multiplication from our previous slide, let's walk through a concrete calculation to see how it works in practice. To find our new vector, we simply distribute that negative 3 to every single component, just as we did with addition and subtraction earlier. Notice how the magnitude has changed and the direction has been reversed because our scalar was negative. We will see how these types of operations are the foundation for the key takeaways in the next slide. Key takeaways. All right, we have covered a lot of ground today, so let's take a moment to recap the key takeaways from this lesson on algebraic operations in component form. First, remember the principle of component-wise operation. As we saw in our step-by-step examples for addition, subtraction, and scalar multiplication, you don't need to worry about the whole vector at once. Instead, you perform each operation independently on the I, j, and k components. You simply deal with the I components together, the j components together, and the k components together. First, remember the principle of component-wise operation. As we saw in our step-by-step examples for addition, subtraction, and scalar multiplication, you don't need to worry about the whole vector at once. Instead, You perform each operation independently on the I, j, and k components. You simply deal with the I components together, the j components together, and the k components together. Second, a very important rule regarding addition and subtraction: you can only add or subtract vectors with other vectors. You cannot take a single scalar value and add it directly to a vector. They are different types of mathematical objects, so they don't mix in that way. Third, let's revisit the condition for equality. For two vectors, A and B, to be considered truly equal, it isn't enough for just one part to match. Every single corresponding component must be exactly the same. That is, the I component of A must equal the I component of B, the j component of A must equal the j component of B, and the k component of A must equal the k component of B. Finally, regarding scaling, when we perform scalar multiplication, the scalar distributes itself across every single component of the vector. As we saw in our calculation with -3, the scalar multiplies the I, the j, and the k components individually. Keep these points in mind as we move into our next slide, where I will highlight some common pitfalls and mistakes to avoid during your exams. Common mistakes. Now, as we wrap up this lesson, I want to pause and highlight some common pitfalls. Even if you understand the formulas, these small errors can easily lead to the wrong answer on an exam. First, keep a very close eye on your signs during subtraction. This is perhaps the most frequent mistake I see. When you are subtracting a vector, remember that you are essentially distributing a negative sign. If you encounter a situation where you are subtracting a negative component, like 2 minus -3, make sure you correctly transform that into 2 plus 3, which gives you 5. Forgetting to flip that sign and accidentally getting -1 will throw off your entire result. Second, be careful not to mix your components. It might be tempting to group all the numbers together, but remember the fundamental rule we've used throughout this session. Components are independent. An I component can only interact with another I component, j with j, and k with k. You cannot add an I component to a j component. They exist in different dimensions. Finally, a very important rule to remember is that you cannot perform scalar addition. You might see a scalar lambda and a vector A and feel tempted to try and add them together, like a plus lambda. However, this operation is mathematically undefined. In our previous slides, we saw that you can multiply a vector by a scalar, or you can add two vectors together, but you can never add a simple number directly to a vector. Keep these 3 points in mind, and you'll be well on your way to mastering vector algebra.